We have part B. Part B should be fairly simple. We don't need to actually write a solution strategy, but I'll give you my ideas as I go. But pretty much, I'm just going to be adding different powers of 2 together. This is 2 to the 0, which is 1, 2 to the 1, 2 squared, 2 to the 3rd, 2 to the 4th, and 2 to the 5th, 6th, and 7th. So 0, yep. So we want to convert this to decimal, so we're going to be adding 2 to the 0 plus 2 squared plus 2 thirds, 2 to the 4th, and 2 to the 7th, which is equal to 1 plus 4 plus 8 plus 16 plus 128. And I'm very bad at math in my head, but we'll try this. 12 plus 13 plus 16 is 29. 128 plus 129 is 7151. 157 in base 10. Similar thing here. We're going to have, this is to the negative 1 power. This is 0 power, 1 power, 2 power. And so we're going to have 1 times 8 squared plus 2 times 8 plus 1. And then we're going to have this plus 4 times 8 to the negative 1. And so we've got 64 plus 16 plus 1 plus 1 plus a half in base 10. So this is going to equal 16 plus 64 is 70, 80. So 81.5 base 10. A2.4 is going to be, we're going to have A times 16 plus 2 times 16 to the 0, which is 1, and 4 times 16 to the negative 1. So A is 10, so that's just going to equal 160, plus 2 times 16, which is 32, plus 4 sixteenths, which is 0.25. So 160 plus 32 is 192.25 in base 10. And now we have part C. And now we're going to be converting from binary to octal. We've already seen how to do that in part 1, so I won't be going into that too much, but basically for the solution strategy, you need to specify that you can parse this into 3 little sections and why you can add leading zeros. Describe fully why leading zeros don't add to the value of this binary number, and then talk about how this 3 is going to convert to 3 in octal, 3 in octal, and 1 in octal. And so the solution is just going to be 1, 3, 3 in base 8. Similar thing here. We're just going to have our divisions. We don't need any leading zeros, fortunately. This is 8. 8 plus 2 plus 1 is B. 4 plus 2 is 6. So that's base 16. Hex to binary. Well, we're just going to need to create a series of 4-bit numbers. So 2 is 0010. F is 1111. And A is 1010. Octal to binary, we've got 7, which is 111, and then we've got 6, which is 110, 5, which is 101, 4, which is 100. That's our solution there. And now, finally, octal to hex. Well, I have 2 options here. I can convert from octal to hex directly, Doesn't seem like a great idea. Doesn't seem very easy. I can convert to octal to another base and then to hex, and then I have, again, two options. I could go to decimal. I'm not a fan. It's kind of a pain. Or you go to binary, which is really easy. And this is the type of stuff you should specify in your solution strategy. And so we're going to break this into a set of 3 bits numbers, and then we're going to go from this binary number that we're going to solve from, octal, into hex, using 4-bit chunks. So the first 3-bit chunk is 0, 1, 0. The next 3-bit chunk is 1, 0, 1. The next 3-bit chunk, again, is 5, so it's 1, 0, 1. And then we have 0. So it's going to be 0, 0, 0. So this is our number in base 2. We want to get to base 16, so we're going to add these little things in here. 0, 1, 0, 1. So that's 5. 0, 1, 1, 0 is 6. And 1, 0, 0, 0, 0 is 8. So this is our number in hexadecimal. And that's it for problem 2.